Okay, so I'm going to begin with an example. So this is a very simple causal model. It says that the amount of wheat grown in a field depends on the amount of rainfall and the acres of wheat planted. In this model, rainfall and acreage are exogenous variables. So, for example, wheat growth depends on rainfall, but rainfall does not depend on wheat growth. And if you've done anything in the social sciences, you might know that typically finding an exogenous variable is a total nightmare. You think something's exogenous, but it's not. But this is about as uncontroversial an example of an exogenous variable you're ever going to find. But it turns out that if we think of these not as just single events, but as things that we're measuring repeatedly, so rainfall year after year, wheat growth year after year, and if we think about a long enough time scale, it could be that over 100 years, 200 years, agriculture does influence climate. At that time scale, any influence of wheat growth on rainfall is so slow and so small that we can just ignore it. Okay, so that's just the starting example, and I'm using it as a way to illustrate the notion of the timescale relativity of causal representations. And that's something I'll be talking a lot about. Now, in addition to illustrating that concept, hopefully this will start to illustrate the broader theme of the talk, which is that the relationship between time and causation in causal models is a lot more intricate than you might have thought. So as I'll talk about, when we're talking about graphical causal inference methods, so people like Pearl, Spiritus, Gleamore, Shyness, Janan was mentioning them, that these methods do not typically infer causal order from time ordering. So that causes precede their effects, plays surprisingly little role in these methods. But when we look at what's going on, many of the assumptions are really assumptions about temporal stability and stable behaviors arising at particular spatiotemporal scales. And the point of today's talk is to show how to use dynamic causal models as developed by Iwasaki and Simon in order to better understand these timescale and stability assumptions. Okay, so let me start saying a bit more about the relationship between causation and time in causal models. What? Yeah, so the reference is In Search of Lost Time Ordering. Shouldn't be competing with Proust, probably. Bad idea, but yeah, so graphical causal inference methods do not build time order into their causal semantics. So, for instance, if we have these two hypotheses, x causes y causes z, or x and z are causes of y, in standard constraint-based methods, we do not distinguish between these hypotheses by saying that if the first is true, then y comes before z, and if the second is true, z comes before y, but rather in terms of the probabilistic implications. So if the first is true, then x and z are independent, probabilistically conditional on y. If the second is true, x and z are independent but dependent, conditional on y. So that is the standard implications of these models. Of course, people will sometimes say that among observationally equivalent models, that you can then use time, but it plays often a very secondary role. And in some ways, I think that this is a really good thing, for reasons going a bit back to Thomas' talk. Because on the one hand, I think it's really philosophically useful to distinguish between time ordering and causal ordering. For example, even if you think that causes always precede their effects in time, you might want to know why is that the case. And if you think that it's just part of the definition of causation that causes come before their effects, then you can't even ask that question. So I think the fact that using causal models, you can understand the probabilistic implications of the causal asymmetry without referring to time is a huge conceptual improvement. But that being said, it's still a bit puzzling how small a role time plays in these models. And you might actually just wonder, well, okay, like how do we actually understand the temporal relations among these variables? And I don't think it's always totally clear. So for example, when I give talks to audiences and I present directed acyclic graphs, so they do not allow cycles, and then someone will ask, oh, is that a problem that you don't allow cycles in these graphs? And then if I feel just like giving the standard answer, I'll say, no, it's not a problem at all, because even in cases where you have apparent cycles, you can just time index the variables. So you think there's a cycle between income and education, because people with more income can get more education and vice versa. But we just need to talk about income at time t equals 0, causing education at time t equals 1, and so on and so forth. And the thing to notice about this response is it just presupposes that when we're given a causal graph, and we haven't mentioned the time relations among the variables, they really do have time relations. We just haven't said what they are, and we can just time index them. And I don't think that's the only option. So again, the time indexing option, the idea is just, well, these variables just implicitly are time indexed. They're what philosophers or metaphysicians would call events. We just forgot to mention when they happened, even though, as Samantha pointed out, that would be really, really useful to know. What I suggest instead is that often what's going on isn't that we're just considering variables that have times, we haven't mentioned them, but rather we're considering variables that in some sense abstract away from the temporal relations among the measured variables. So here's to give just some sense of what I mean by that. Imagine we have some vector of variables. Could, for example, be a time series. Well, depending on what assumptions we make, we might be able to represent this vector of measured variables as a single variable for the data generating process. So for example, if we have a stationary time series, then time order doesn't matter. So we might not need to keep track of which variables come before others in the ordering. I mean, to think of a really simple case, if all of them were generated by some variable which was a mean plus a time stationary error term, then you could just have a single variable for the data generating process, even though you can measure it at different times, because time isn't making a difference. In the event you have non-stationarity, it becomes more complicated. And my point here isn't that you can't do causal inference with non-stationary time series, just it becomes more complicated. And in general, I'm just restraining myself. I'd love to talk a lot more about time series, and if anyone does want to talk about it, either in the Q&A or after the talk, very glad to. But the point here is just to give you a sense about what I'm suggesting when I'm suggesting that we have a model where we've just represented some variable like pressure or temperature or height or whatever, it doesn't matter, and we haven't mentioned the time, and it's because in some sense we've made some temporal assumption that allows us to abstract away from the temporal relations among the measured variables. And stationarity could be one such assumption. Now, more broadly, I think that there's a historical reason for why it is that time is omitted from causal models in this way, and I think it has to do with the development of causal models as part of econometrics and as part of the structural equation tradition. And at least historically, the earliest applications of these tended to be to systems at equilibrium or with relatively stable time stationary dynamics. And I think that history of the development of causal models as part of this tradition still influences it. Now, if you accept this story, I haven't really given you much evidence for it, but I'm going to put it on the table as a story. We might think about then the dynamic causal models that I'm going to talk about are going to be a generalization of standard causal models, because while standard causal models consider a system at equilibrium or steady state, dynamic causal models generalize to consider the behaviors of the system away from equilibrium. And the upshot of this philosophically is that even though what I'll be talking about in the next few slides is about the relationship between equilibrium and dynamic models, and that might seem really, really obscure, like, okay, maybe some weird causal modelers care about it, but serious philosophers or metaphysicians don't. I'm suggesting that even when people do not explicitly talk about equilibrium and dynamics, the types of assumptions I'm considering are often embedded in the models and not made explicit. Okay, and the last part I'm just gonna, I'll skip because I'll come back to that. Okay, and then last preliminary, so I'm talking about timescale, and one way we can understand is operationally, so we're sampling some quantity repeatedly, and we can think about considering the system at a longer time scale as sampling at a slower rate. To consider it at a shorter time scale, let's sample it more frequently. And when I talk about considering a system at equilibrium, I'm imagining that we're considering it at a time scale at which all the variables have reached steady state by the time they're sampled. And to be totally clear, we could talk about equilibrium and dynamics without ever explicitly talking about timescale. But it's helpful in cases where we want to model a system as having a steady long-term equilibrium or tending towards a steady long-term equilibrium, and then modeling transient dynamics as perturbations from the equilibrium. There's going to be a relationship between the equilibrium dynamic and longer, shorter timescale distinction. Okay, so in the next part of the talk, I'm going to now just give you the basics of dynamic causal models. And I'm going to go all the way back to Herbert Simon, 1953, causal ordering and identifiability. And if you get nothing else from this talk, we should all be reading a lot more Herbert Simon. That's just one of the takeaways. It's never hurt anyone. Okay, so Simon's wondering, at least in my retelling, where does the causal asymmetry come from, given that many of the basic equations of sciences have no built-in asymmetry? So paradigmatically, here we have the ideal gas law, relating the pressure, volume, and temperature of a gas at equilibrium. This is just an equation. That's just an ordinary equal sign. So this doesn't tell us whether pressure causes temperature or temperature causes pressure. So where does the causal asymmetry come from? Well, Simon says, even if we don't get causal direction from this equation alone, if we add additional facts about the system, we do. So if, for example, there we go, we say that it's in a heat bath maintained at a constant temperature, and for example, that's a fixed volume system, well, now we get that temperature and volume are exogenous, and from the values of those variables that are exogenously set, we can determine the value of pressure. And the basic idea behind causal ordering is that the causal ordering, what causes what, corresponds to the order in which we solve for the values of variables in the equations. And just to be really clear here, there's no magic here. This is not telling us how to get causal conclusions without causal assumptions. So to say that temperature is exogenous, that's a causal assumption. But it's just making a bit more explicit where we get this directionality from. And of course, we could have a different setup. So it could be the case that it's a movable piston. So now volume is not fixed, but equilibrium pressure is. And now we're going to get a different set of causal relations. Importantly, when you can do this solving for the causal ordering, well, then you can rewrite the equations as ordinary structural equations. So the type of stuff that we all know and love. You can give them a causal interventionist interpretation. You can add error terms, and they automatically satisfy causal Markov. So from this basic framework, you can get all the stuff that everyone's more familiar with, but with an earlier starting point. Okay, now why this matters for us really has to do with this later paper with Yumi Iwasaki, where they claim that the initial causal ordering method was initially defined only for static systems consisting of equilibrium equations. Now, Simon had never really explicitly said this, but certainly you can see that in the example I talked about, we're considering all of these equations at equilibrium. Also, historically, Simon was dealing often with the simultaneous equations tradition from econometrics. And you might wonder, well, how can you have simultaneous equations if causation is not simultaneous? And the way I'd suggest we think about them is not that there has to be simultaneous causation, just that we're considering the system at a time scale at which the variables have had sufficient time to respond to any perturbations and reach steady state. Okay. So now, next few slides, this is the technical part of the talk. And here I really just want to show you how these models work and the basic operations involved. Okay, so we just saw an equilibrium representation, or in fact, two equilibrium representations for the two different ideal gas systems. Here I'm just throwing at you a dynamic causal model. I'm going to unpack this a bit. So basically, we're now considering a model where we're not assuming that volume has had time to reach equilibrium. So we're starting by thinking about a movable piston system. Here we have a mass on top of the piston, which is there's then a force on top of the piston, which along with the force in the bottom of the piston influences the acceleration of volume. Now these dotted lines, these are integration links. And integration links reflect the fact that if you know a higher order derivative of a variable, then you know its current value, then you can derive its value at the next time step through integration. So this is just integration in the sense of the inverse of differentiation. So these dotted lines, the integration links, they're going to bring time into the causal model. And one thing that's kind of subtle here is that because you need to specify initial conditions in order to apply integration, the initial values of variables that are away from equilibrium are going to be exogenous. So the dynamic causal models will tell us how a system evolves from initial conditions, but you're going to need to specify the initial conditions. And this is going to be different than just an equilibrium causal model. So yeah, and we include time derivatives and integration links only for the variables that are considered to be away from equilibrium. Okay, so in any case, we have now volume not at equilibrium. Volume and temperature cause pressure, which influences the force in the bottom. And just to see how the equation approach works, it works in basically the same way as the original causal ordering method, except we have some more exogenous variables, because first of all, we've added mass, and also the initial conditions are exogenous. And then we solve for the equations in the same way. So mass determines the force in the top, and the ideal gas law gives us pressure from volume and temperature, and then the force in the bottom is proportional to the pressure, and then using Newton's second law, we combine the forces in order to get the acceleration. Okay, so that's the basic model. Often when I show this to scientists, at least the scientists that are willing to listen, this is way too much. They don't like the cycles. It's really kind of scary. So just if it makes you happy, you can also unfold this in time. Basically treat all the variables connected by ordinary causal arrows as simultaneous. And the integration links as giving you cross-time step causal relationships, and you can unpack it in this way. And one thing you notice is that even though there's a cycle in the dynamic graph, it's not technically cyclic. And yeah, so if this graph helps you understand things better, great. Notice that we're still not using time ordering to solve for causal ordering. The really crucial information contained in this graph isn't that we're looking at what precedes what and using that to solve for the time ordering. What really matters is that we have these clusters of variables influencing one another at different rates, such that clusters of variables that are very tightly connected and influence one another quickly at a time scale, those are influences simultaneous, and influences that are treated as taking time over that time scale are treated diachronically. So this type of representation is capturing timescale separation facts as opposed to using the time order to solve for the causal ordering. Now, most importantly for us today is when you use the compact, not rolled out representation, you can apply an operation known as equilibration. And equilibration is when you take a variable in a dynamic graph that has not reached equilibrium, and you apply equilibration to determine what the equilibrium graph will be. Okay, so this works as follows. So first you set all derivatives of volume to 0, remove them from the model. You also delete all equations going into volume and remove their derivatives. This includes the integration equations. And then you remap using the causal ordering. And perhaps unsurprisingly, when you do that, you end up with one of our initial causal models, namely the one in which pressure and temperature cause volume. I'll say a bit more about that, but again, the important thing here is that equilibration takes a model in which you had a feedback loop, and you derive the model that would result from equilibrating that feedback loop, so allowing the system to run to equilibrium as a result of self-regulation. Okay, much more familiar is the notion of intervention. So that's just the do operator. And, sorry, gave away the punchline. And the only sort of surprise here is that when you intervene on a variable with derivatives in the model, you also intervene on its higher order derivatives. So the thought of something like you can't intervene on the position of an object without also setting its velocity and acceleration to 0. Okay, so when we do that, we get a different model. And in this particular case, we saw that with the dynamic model I gave you, if you intervene, you get one model, the one corresponding to the fixed volume system. If you equilibrate, you get a different model, the one corresponding to the movable piston. And without going too much into the details, the fact you get these two models has actually been a source of lots of consternation. So Denver Dash, in his dissertation, he thought that this was really a problem with equilibrium models for reasons that I'm not going to really go deeply into. What I want to argue is that actually it's the right result that we get these two different equilibrium models. And the reason is that basically what equilibration is telling you is what happens if you allow the system to reach equilibrium via a feedback loop that allows it to self-regulate. Now, when you, in contrast, intervene on volume, you're not allowing that feedback loop to operate. And as some of you probably know, feedback loops are necessary to obtain certain types of stability. So when you intervene on the system, and when you intervene not just temporarily, but hold volume fixed, you're not allowing the feedback loop to operate. You're destroying the stability producing property of the system, and you're bringing it to a different stable state, the one corresponding to the fixed volume container. So I think what's going on here is that we just have these two systems that with two relations, and the interesting result is that intervening and equilibrating just bring the system into two different incompatible states. Okay, so that was the main technical parts. Now we can sum up how this relates to timescale. So first of all, so we saw equilibration, which once again, it takes a feedback loop that in one model reflects a variable that has not reached equilibrium, and it involves treating the reaction time as if it were instantaneous. Now there's another operation, which I'm going to describe, called exogenization, which involves treating a variable that's changing extremely slowly as if it were constant. And using the timescale picture, we could think about these operations in terms of zooming out and zooming in. So equilibration is when we zoom out to a timescale at which something that at the previous timescale was taking time to occur, but we zoom out and we can treat it as instantaneous. While exogenization is we have something that's changing at a timescale, and we zoom into a timescale at which the rate of change is so slow that we can treat it as constant. Now going back to our original example, we can now understand it in terms of exogenization. So once again, we had this case where we had one model without a cycle, and where rainfall was exogenous, another one with a cycle. And it's a very simple example, but the punchline is that exogenization is the operation that allows one to treat rainfall as exogenous. And the big takeaway of that for timescale is that Iwasaki and Simon's dynamic causal models provide a framework for capturing this timescale relativity of causal relationships. So these operations allow us to understand the relationships between causal models at different timescales in a systematic way. And one thing to note is that the relationships can really look very different at the different timescales. Okay, now the rest of the talk, I'm going to quickly do some implications, because really what I want to do in this talk, I mean, again, I'm happy to talk about the technical details with anyone who wants to get into them, but I really think that this whole framework and this whole way of thinking, both in terms of timescale and stability, it introduces lots of things into the philosophical and scientific study of causation that, at least as far as I could tell, other people aren't talking about. And I really just want to convince you all that you should actually think about it as well. Okay, so here are some implications. First one is philosophical. So, as Cartwright told all of us, no causes in, no causes out. I agree with Cartwright on this. And that means, for example, you can't define something like exogeneity without causal assumptions. And I, again, totally agree with that. But I think sometimes people use that as a way to end the conversation and say, like, okay, well, then there's just nothing we can say. You just, you say, how do I know this variable is exogenous? And they say, like, look at your scientific theory or something. And you go, well, thanks so much. I have no idea. And I think that we can say more about it. And I think seeing how assumptions such as exogeneity vary with the time scale at which we consider system does tell us something about how the world is and needs to be in order for us to make these assumptions. So we can see, for example, that in this simple crop example that, well, we're saying it's exogenous, and we can allow that the world's more complicated, but if we genuinely think the influence is minor and slow acting, that would be a legitimizing assumption for treating it as exogenous at the time scale. Additionally, I think this does have some payoff for some philosophical debates, including engaging with people like Janan. So the previous talk sets this up nicely. So one thing Janan writes about in How Causes Depend on Us is building on the Pearlian picture she referred to. There's this idea that causal relationships are relative to the choice of exogenous and endogenous variables. And she has her own story about how this choice does depend on features of agency. And I'm not going to really risk saying anything too ambitious in this short talk, but I'm just making the claim that having a general theory, a theory of the type I'm providing of what it is in the world that allows you to think systematically about exogeneity will also allow us to continue that discussion. And similarly for discussions that have come up in several of the talks about is there causation in closed deterministic systems, where you sort of reach a standoff because, again, going back to Janan's talk, we understand in open systems what the exogenous factors are, but let's just kind of generalize out and think about the universe as a whole, and we can define exogenous sources of variation. We don't know what they refer to in the world. And again, I just think having more resources to not just stipulate that certain things are exogenous, but also think about, in cases we understand, what are the features of the world that allow us to treat it like such, seems to me like a way to advance this discussion. Something else, this is more on the modeling side. So there's lots of debates about causation in complex systems. And here I'm just going to quickly illustrate, again, without giving the details, of how we can use these types of models to really think about some standard complex systems. So one that gets talked about a lot, especially in cognitive science, is the Watt governor. So this is a device for regulating the speed of steam engines. The idea is that people were using steam engines to do work, say hooking them up to a loom for weaving. You want them to do regular work, but the work sources are not constant. There could be changes in the workload, changes in the coal. So this was a device that, instead of having to have some human there, as you might think, who would see the changes in workload and respond to them, this is a controlled feedback loop where what happens is you have these fly balls, which have a mass that are connected to a spindle. And if, for example, and then the spindle is rotating proportional to the speed of the steam engine. If, for example, the steam engine starts to speed up above the desired value, the fly balls start to go out due to the centrifugal force. And then the spindles are hooked up to the throttle valve in a way that as the fly balls go up, the valve is slightly shut. So you get a negative feedback loop, increases in speed above the desired value, cause the system to automatically slow down, let less steam into the engine, and vice versa. So this is, again, widely discussed in cognitive science especially. It's also just a kind of paradigm example in at least mathematical discussions of dynamical systems and control systems. In reality, people don't use this design so much anymore, but that's but it's a nice mathematical model. So if you're ever in Munich, you can also see lots of them at the Deutsches Museum. So in Van Gelder's seminal discussion of this as a sort of model of dynamical cognition, he makes the claim that when we understand the behavior of the Watt's governor, the system's entire operation is smooth and continuous. There's no possibility of non-arbitrarily dividing its changes over time into distinct manipulations, and no point in trying to do so. So here, he's giving an argument against why what this system is doing shouldn't be understood using a computational model. That's obviously not what we're talking about today, but I think this type of argument, or this type of perception of complex dynamical systems as being such that every part influences every other part at the same rate irreducibly, also is the type of argument you see people giving against causal interpretations of dynamical systems. And therefore, it's somewhat significant that when you actually try to model the system dynamically and causally, you see that, in fact, it is not such that you can't decompose it. And in fact, you can give a causal model of the sort I've been giving. So basically, and without getting into the details, you have this causal model showing how theta, the angle of the arms, depends on gravity, length, and the speed of the engine, and how the angle of the arms determines the steam let into the engine. P is the workload, and those determine the change in speed. So this is just an example of how to use these types of models to model a slightly more complicated dynamical system, and hopefully give you some confidence that we can generalize this, because these types of feedback loops are not rare. So this system is still relatively simple, but the use of control feedback loops is not, and here we see that you are able to model it causally. And as with the previous part of the talk, I'm not going to make some huge sweeping claim about what this tells us about causation in dynamical systems. I'll just say that this is the type of example lots of philosophers are talking about, and people are making claims about causation and complexity. And as far as I know, no one has actually tried to causally model it and show this could be done. So as with other parts of the talk, I just think there's a lot of opportunity here to take a lot of what philosophers are doing informally and to think of it more rigorously. And I'll just say that through the process of building this model, I learned a lot about the system that I had not gotten from the philosophical treatments. I do think it's illuminating. Okay, now in the last implication, I'm going to talk about stability, because once again, a feature of these models is that looking at the feedback loops in the dynamic model can allow us to see the stability ensuring mechanisms underlying some more stable behavior. And I think stability is one of those things that really has not been talked about enough, at least not in this way, in the context of causation. And I think this is going to be a payoff that also has lots of practical implications. So for one thing, lots of interventions we care about, they're not just trying to change the value of a single variable, but really trying to get a system to be in a new stable state. So one example of this, at least if I'm understanding it right, would be chemotherapy. So not knowing the underlying science, but I take it what you're trying to do is you start with a case where where the immune system is not such that it is able to eradicate the cancer, and you want to apply chemotherapy to weaken the cancer to the point that then the immune system can take over. So what you're trying to do is change the dynamics of the system so that once you remove the therapy, it will have a different stable state and one that is hopefully more favorable to the patient. I also put in therapy here. At least some types of talk therapy are also trying to change your patterns of behavior so that you end up in a different stable state as opposed to the ones that make you more miserable. So I think to just characterize what the goals are of many interventions, we do need to talk about stability, and that many policies shouldn't be considered successful unless they actually produce stable solutions and not just bring about an effect. And I think a discussion where this would really help is the discussion of causal extrapolation. So this is the question of how to infer causal relations across populations. You find out that a certain education policy worked in one place. Will it work in another? Very often it doesn't. And many people, including Nancy Carter and Jeremy Hardy, have talked about these types of inferences. And the type of treatment they, and again, it's not just them, everyone pretty much gives, are fairly static representations. So they talk about background factors. Here they have in mind Mackey's Innes conditions, where the idea is, well, you have these different populations. If it's, say, a teaching context, maybe one population has a better supply of teachers, the second population does not. So that's why the cause didn't generalize across the populations, because one of them had the necessary background factors, while the second one did not. And what I want to suggest is that even when we're considering single populations, so before you get to extrapolation, does this cause generalize? We shouldn't just think about some static set of factors. If you're designing an educational policy and you're hoping that the kids will do the homework, that would be helpful for the policy. But it should be the case that if you discover that in a particular area kids are not doing the homework, that there should be some mechanism that detects that this is happening and implements a feedback loop to shift the policy to correct for that deficiency. So to think about a policy succeeding, we want not just to happen to succeed, but also to be dynamically stable in light of possible perturbations. And I think if we started modeling that, which I think requires dynamic models, that would also help understanding how we are not just lucky when we get generalizability. Okay, so just to conclude, so first of all, I've argued that many basic assumptions of causal models are timescale relative. I think timescale relativity is hugely important and presents both philosophical opportunities for understanding the conditions of attribution of causal models and for also doing better causal inference and policy evaluation, and also that the notion of dynamical stability is different than the notions of stability that exist in the literature because most of the existing discussions are implicitly considering static models. So thank you very much.
Hi, thanks for the great talk. So when you do these model transformations, going from a lower level causal model through, I think you called it exogenation, and I forget the other one.
Equilibration.
Yeah. Is there a change in the kinds of questions that you can ask, the kind of inference queries you can pose against the abstracted model? And is there a change in the accuracy of the inferences, right? If you're making these assumptions about, this being a steady state, it seems like there might be some loss in accuracy. And so is there a precise way in which you can know what that will be?
Yeah, that's a great question. And the answer is ultimately yes, there can be a loss in accuracy, but I'll have to be precise about what that is. So I do think, and it's been important for me to argue that the models are correct in the domains of, or at the scales of interest, and to at least, so in my intervening and letting go paper, I explain, because you actually do need to revise some adequacy conditions in the causal models, but at least I've argued that could be done. But there is a loss, and the loss is basically that if you have a system that intervening on certain variables will destabilize it, you're not always going to be able to see that at the larger time scale. So the dynamic model will you'll see the feedback loop, you'll know the result of intervening, while other models, because you're just not zooming in enough, you won't be able to see that. So that is a loss, and yes, and I think it's an argument for doing more work on dynamic modeling and exploring it, but again, part of why I do want to argue is even if that's helpful to do, we can still understand models in their own terms, because at the end of the day, I think we're always at a time scale. So we're never going to get to the bottom level. So we better have a story about why, why at least we can understand models as being potentially legitimate at different time scales, even if, like any model, they might break down sometimes.
Thanks so much. So there was something that a lot of what you said just resonates with thinking about practice in physics, where you want to understand stability under perturbations for any system you're looking at, and you want to try to look at different timescales to see if there's things that you have to take into account if you're really trying to extrapolate over large scales. And I was curious how you'd characterize the contrast between the way that dynamical causal modeling approaches those, that distinguishes it from just the sort of standard techniques if you just had a partial differential equation and you're looking at stability and perturbation analysis.
Awesome. Thanks so much for your question. And one thing just to say, so I think the one person I've seen, and maybe there's a bunch, but the one I've come across who I think really does get the stability right in the context of physics is Yemima Ben-Menachem in her Causality in Physics book. And she also has some interesting things to say about stability and historical explanation. So I'll throw that out there. In some ways, they might not be all that different, or at least here's one thing that can happen when you find yourself modeling something like the governor. And so something like equilibration, it's not radically different than what you do when you have a set of differential equations and you solve by setting something to zero. And in that sense, on the positive side, it creates a continuity between differential equation practice and causal modeling. On the other hand, you might be inclined to say, like, look, everything you were doing, I could have just done with the differential equations. And it's a discussion we need to have whether that's in fact true. I mean, for me, the continuity is a good thing. And I guess I'd say at least this, because it's a longer discussion. So first of all, I don't think that my discussion says anything general about whether dynamic systems in general can be modeled. What I've shown at best is that when you have dynamical systems that can be written in a certain canonical form, they can also be interpreted causally. Now, whether that's, in some cases, that might not contribute that much to the modeling practice, but philosophically, I do think it's important because you see so many claims about, again, not being able to have causation in dynamical systems, and here we see that the analysis is similar. Now, in terms of what we learn, I think it creates a bridge where you can argue either way. You can argue that fundamentally the assumptions in the differential equations model they thought of were non-causal assumptions are causal assumptions, or you can go in the other way and say, look, the causal is just a unhelpful abstraction from the differential equations. You probably know which way I want to go, but yeah, that's a longer discussion.
So Chris, we have, Ben Hanim was part of a discussion, so the video is available on the website if you go. So I have a very quick question before the next speaker comes up to set up, and that is, we can treat these exogenous factors, right? So in the rainfall wheat example that you showed, because they operate on completely different time scales, right? So there's sort of a decoupling of time scales. But underlying that, isn't there an additional assumption as well that the variations on that other time scale that imposes on the system are really small? Right? When we are studying on the time scales that we have chosen to study, the variations on not only is the time scale longer, but the variations that it can produce in the system are very small over the interval of study, because we're choosing to focus on a particular time scale, right?
That sounds right.
Yeah, okay.
Yeah.
So that's an additional assumption that
Yeah.
it doesn't have, okay.
Yeah.
Great, thank you so much. Let's move on to our next speaker.